Howdy, so this is the second part of the second day of lecture, and in this video we're going to be talking about friction. And we've got two types of friction we want to cover today. First is static friction. What that means is that we push the object, it's on a surface, we're pushing it, and it doesn't move. And the second type of friction that we're going to be talking about is kinetic friction, which is that now the object is moving and the surface is either bringing it to rest, or perhaps we're pushing the object and it's moving and the surface still opposes the motion, so we're not getting as much out of our applied force, or the force that we're applying as we'd like to because friction is opposing us. And it turns out that both types of friction can be treated using the same equation, which is F equals mu times N. And the mnemonic we use to memorize that is that friction is fun. We're actually not interested in the truth of that statement. We're going to use it to kind of help us memorize this. So first, this is the kind of situation we're talking about. So we're going to have an object resting on what we call a real surface. And what I mean by a real surface is that, you know, when you first start forces, everything's frictionless. And of course, when you go out in the real world, everything has friction. So we're being a little circular here. But what we mean by real surface is, well, it's going to have friction. So we get a surface like this, and we're going to put a box on it. And let's say, for example, that we apply a force to push this box like this. So there's a force. And what we're saying here is, in this situation, let's say it doesn't move. So I'm pushing with a force F, and the box simply doesn't move. And of course, if we were to draw a free body diagram of the situation, what we'd have is we'd have a point representing the box, and we'd have our usual normal force, and we'd have our weight, and of course we'd have our applied force F. And now what we're saying is that there is actually a force going backwards, and I'm going to label it little letter f, and I'll put a subscript s on it to mean static. And what we're saying is that there is a force here that prevents the motion of the block that's actually caused by the surface rubbing against the block to keep it from moving. And we call this static friction. The static, again, means it's not moving. That's the first kind of friction. Now, the second kind of friction that we encounter, it's kind of sad. It's sort of the identical situation. We're going to have a box, identical setup, but the outcome's different. So what's going to happen is we're going to push the box, and we're going to say that it does move. Let's say we draw the free body diagram. And in fact, what's interesting is the free body diagram looks very similar. We're going to have a force here, and we'll have a friction force here again, and of course we label our normal force on the mass due to the surface and the weight of the mass due to the earth. Again, it's mg. And what's happening here is we call this Fk. So the free body diagrams look very similar. Actually, I should have made these two arrows equal in length. So these two arrows that I've kind of drawn little blue things here to sort of point at them for you, they should have the same length because they cancel each other out. But here, what's happening is we have this kinetic friction, and it's not big enough to overcome the force that I'm applying. So the box does move, but not as easily as if the surface were smooth. There is another circumstance where friction can occur, which is that suppose I have a box that is actually moving, and I'm going to draw the velocity using a completely different color. Let's say it's got a velocity v0. I draw it in orange because I don't want you to think it's a force. If we were to draw the free body diagram, so let me just kind of do something here. I'm going to call this situation Roman numeral 1. And in situation Roman numeral 2, what's happening is we have the box moving. But let's be careful. What's going to happen is we only have the kinetic friction bringing the box to rest, and we have the normal again, and the weight. So this friction, it does two things. If I'm applying a force to get something moving, the kinetic friction while the thing's sliding opposes the force that's pushing it. If the thing is already moving, what kinetic friction does is it actually acts as a force to slow the object down and bring it to rest. So there are some fundamental differences between static and kinetic friction. Not just, and it's easy to say, oh, well, static is for not moving, and kinetic is for moving. And yes, that's true, but there are a couple of fundamental differences. Now, the thing with friction is that it's actually a very, very difficult force to understand on an atomic level or on like a materials engineering level, if you want to, and I know I misspelled that, sorry. But it's very hard to understand it on a very, very basic level, like what's actually happening in the atoms and the molecules to bring friction about. So what engineers and scientists did is that they just sort of observed a relationship between the friction on an object and the normal force pushing up on it. So on this force right here and here. And if we scroll up, right here. So what they noticed was they could sort of make up, not make up, but they noticed a relationship between the friction force that opposes motion and the normal force that a surface pushes up with. And they came up with a proportion. They said, well, the friction force is usually equal to a measurable constant that we're going to call the coefficient of friction times the normal force acting up on the object. And what they did was they said, well, we're going to define, since we notice there's the friction of an object standing still and the friction of an object moving, we're going to actually name two different coefficients. So we have the static friction equals mu static times the normal force acting on an object, and the kinetic friction is mu kinetic times the normal force. And it's not just that we are trying to distinguish between the friction of not moving and moving. It actually turns out that there are slight differences in how these frictions act on objects. The key difference, and this is very important for AP Physics, is that it turns out in almost every single case, and I'll say this tentatively, in every single case that we are going to study in AP Physics, we will notice that the kinetic coefficient of friction is always less than the static coefficient of friction. And the thing is, this actually has real implications. Let's look at the real implication of this remark. What it means is, it's hard to get something moving on a surface because the static friction has a big coefficient. But then once it is moving, it takes less force to keep it moving than it took to get it moving in the first place. I know that's bad handwriting, but whatever. So, again, it's hard to get something moving on a surface. Once it is moving, it takes less force to keep moving than it took to get it moving in the first place. So what this means is, suppose I have an object just sitting on a surface like this, and I apply a force. Let's actually talk about what happens. So what's going to happen is I'm going to actually do a graph of the friction force versus the applied force. So what happens is that when I start pushing this box, I apply no force, and then what's going to happen is I'm going to reach a maximum value of mu static. So here's what's happening. Suppose I push a box, and I push harder and harder, and with more force, and with more force, and with more force, and then it gets moving. Okay? Let's talk about what happens. So what's going to happen is the friction force exactly balances the applied force. Okay, so they're exactly equal. Then I reach this threshold where the friction force exactly equals mu times the normal force. Once I push beyond this, I get the box moving. And so to keep it moving, it actually turns out that I only need an applied force equal to mu k times the normal force, which is what this value is here. So I have to push to get it moving, and then once I get it moving, I don't need as much force, so I can actually push with a little bit less force, and that's what will keep the object moving. That graph might seem a little bit confusing. We'll go over it in a little bit more detail later. So we have this block right here. Let's draw the free body diagram, and we're told that there's some kind of friction force on it. We have a mass of 3 kilograms. We're told the coefficient of static friction is 0.2. What minimal force gets the block moving? So I should say start the block moving. And then once I get the block moving, what's the acceleration of this block if this minimal force has been applied? So first, let's start with the free body diagram. I'm going to have the normal on this mass due to the surface, the weight of this mass due to the earth. I have the applied force, and I have the friction force. And I'm not going to label it S or K because we're going to actually change this as we do our equations. So let's be clear and set up our equations. So for part A, we're going to write that the normal force minus the weight equals 0 because nothing happens in the y direction, so those two forces cancel. So in other words, I have that the normal force actually equals mg, so we're going to use that in a second. Now, what's happening in the horizontal direction? What happens in the horizontal direction is we want to know the minimal force to start the block moving. So in other words, we're just about to get the block moving, but we fail to actually make it happen. Okay? So what that means is we have the applied force to the right minus friction, static friction to the left, and the effect is those two forces cancel. So let's solve for this force. We know that the force equals the static friction. The applied force has to equal the static friction for those two to just barely cancel. So now I'm going to use the fact that friction is fun. Friction equals mu n. So what that means is I'm going to plug in mu surface times mu static, times m times g. So I'm just doing this substitution from here into here. And that's how I get that answer. So that's the minimal force to get the block moving. We can actually calculate that right now. So the force would be 0.2 times m, which is 3, times 10, which is g, right? You can use 9.8 or 10. I'm going to use 10. So that means we're going to have 15 newtons worth of force when we do this calculation. Now for part B, what we're saying is, well, if this minimal force has been applied and we just barely get the block, so we're able to get the block moving, now what's going to happen is once the block is moving, it's going to be easier to keep it moving. We actually don't need 15 newtons of force to keep it moving. But let's say that we have applied this 15 newtons and it's moving. So we actually have the same free body diagram, but let's be clear. We still actually have almost identical equations. We're still going to have the normal force, canceling the weight, and we're going to have the normal force then equals mg. But now look what happens in our second equation. It's a little bit different. We're going to have F minus F kinetic. And now these forces don't quite cancel. We get mass times acceleration. The block actually accelerates. So let's plug in what we have. I'm going to use letters here. So our force actually has a value of mu s mg. If you liked, I guess you would have put in 15 newtons if you were using numbers, but I'll just use the letters to get you used to that. Minus mu k mg, because this is the kinetic friction, and the effect is ma. So what we actually get is that our acceleration, when we cancel all this, is going to end up being mu s minus mu k times g. This is AP Physics, and we skip a lot of algebra. So what this means is we're going to get 0.2 minus 0.1 times 10. So our acceleration ends up being 1 meter per second squared. Okay, so notice I'm doing this a little bit different than AP, or than regular physics. This is something we're going to need to get a little bit used to. Now, for your last thing on your homework assignment, what I'm actually going to have you do on Google Docs is I want you to do a similar problem, but here's what I'm going to say. Let's say that F is 20 newtons. Let's say that M1 is 2 kilograms and M2 is 3 kilograms. And we'll make mu static equal to 0.2 and mu kinetic equal to 0.1.